In April of 2013, in a paper in the Astrophysical Journal Letters, an astronomer at Pennsylvania State University named Howard Bond and his collaborators announced something that, for a brief period, made the popular press ask whether the Big Bang was wrong. They had measured the age of a single star in our own galactic neighbourhood with unprecedented precision. The result at the central value was 14.46 billion years. The universe itself, by every other measurement we have, is 13.787 billion years old. The star, taken at face value, was older than the universe by about 700 million years. The star is called HD 140283. A subdwarf in the constellation Libra, about 200 light-years from Earth. Just bright enough to see with binoculars on a dark night, and, by every measurement we have ever made of it, one of the oldest individual stars in our own neighbourhood. If you find that as fascinating as I do, hit subscribe, pour yourself something warm, get comfortable, and settle in. Because tonight, we are going to walk slowly through the strange story of HD 140283, how it appeared older than the universe, what that actually meant, and how the resolution rewrote some of how we measure stellar ages in the first place. Now, let's ease into it. Part 1. The neighbour star nobody noticed. Here is the kind of star HD 140283 is, in physical terms. It is a subdwarf, which means it is a star in roughly the same temperature range as the Sun, but slightly less luminous, with an evolutionary status that is just beginning to leave the main sequence. The mass is about 78% of the Sun's. The surface temperature is about 5,750 Kelvin, just slightly cooler than the Sun. The luminosity is about 4.7 times the Sun's. The size is comparable to the Sun's. None of these properties on their own would attract particular attention. The distinguishing feature, the one that placed HD 140283 at the center of stellar astronomy in the early 2010s, is its chemistry. For most of the 20th century, HD 140283 was, in catalogues, simply a number. It had been observed by various surveys since the late 19th century, when the Henry Draper catalogue first listed it under the designation that gives it its name. HD stands for Henry Draper, the American physician and amateur astronomer whose widow funded the catalogue project after his early death. The number, 140,283, was assigned by sequence as the catalogue was compiled. The star, in the early catalogues, was unremarkable. Here is the catalogue history that placed HD 140283 in the modern record. The Henry Draper catalogue itself has an unusual history. Henry Draper, the namesake, was an American physician with a passionate interest in astronomy. He had been one of the first astronomers to photograph stellar spectra in the 1870s using the new wet plate photographic technology. When he died unexpectedly in 1882 at the age of 45, his widow Mary Anna Draper devoted the rest of her life to funding astronomical research in his name. The Henry Draper Memorial Fund supported work at Harvard College Observatory for decades, and the catalogue itself was the principal publishable product. By the time the catalogue was completed in 1924, it contained spectroscopic classifications for 225,000 stars, the largest such catalogue ever produced. The work was led in significant part by Annie Jump Cannon, who personally classified the spectra of more than 250,000 stars during her career. Cannon's classification system, refined over decades, became the standard scheme used worldwide and is, in modified form, still used today. Without her work, and the work of her colleagues at Harvard, the modern era of stellar astronomy would have begun much later. HD 140283, like every other star in the catalogue, owes its modern designation to her labour and the broader Harvard program. The Henry Draper catalogue, originally compiled at Harvard College Observatory between 1895 and 1924, was, in its time, the largest and most comprehensive stellar catalogue ever assembled. It contained spectroscopic classifications for roughly 225,000 stars drawn from photographs taken at Harvard and at its southern station in Peru. Each star was assigned a number in sequence as the catalogue was compiled. HD 140283 received its number somewhere in the middle of the catalogue's compilation, with no special distinction at the time. The star's spectral classification in the original catalogue was simply listed as a particular type of subdwarf, without any indication that it would later become one of the most famous individual stars in the literature. It was a faint star in the constellation Libra, between the brighter constellations Scorpio and Virgo. It was, by every measurement of the early 20th century, just one of the millions of catalogued stars in the sky. Its apparent magnitude is about 7.2, which means it is just below the threshold of visibility for the unaided human eye on the darkest nights, but easily visible through a small pair of binoculars or any backyard telescope. Most amateur astronomers, even those who knew their constellations well, walked right past it. It was, by every standard reckoning, an ordinary catalogue object. The Henry Draper number, 140,283, did not stand out among the hundreds of thousands of other catalogued stars. Each catalogue number was just a sequential identifier, with no special meaning beyond order of compilation. The star happened to have a number near the middle of the catalogue's compilation range. Other stars with neighbouring numbers were similarly unremarkable. There was nothing in the catalogue itself that distinguished HD 140283 from the rest. It would take subsequent decades of work by many different astronomers and many different teams to gradually identify the star as something special. The position in Libra was unremarkable. The brightness was modest. The classification was nothing special. For 30 years after the catalogue was completed, nothing about the star drew particular attention. Here is what changed in the mid-20th century. The thing that began to change the picture in the 1940s and 50s was a careful look at the star's chemistry. Spectroscopic observations of HD 140283, taken with the increasingly precise instruments of mid-20th century stellar astronomy, revealed something genuinely unusual. The star, when its spectrum was analysed in detail, contained almost no heavy elements. Its iron content, the standard reference for stellar metallicity, was less than 1 part in 250 of the Sun's. Other heavy elements like carbon, magnesium and silicon were correspondingly low. The pattern, taken across many elements, was consistent with formation from very early gas, before much chemical enrichment had occurred. The star was, by composition, almost entirely hydrogen and helium, with only the faintest traces of anything heavier. That property, on its own, was significant. Here is the underlying mechanism that drives this enrichment. Stars in the present-day universe form from gas that has been progressively enriched over billions of years by the supernovae of previous generations. When a massive star reaches the end of its life and explodes as a core collapse, supernova, it scatters its outer layers, including the heavy elements it has produced through nuclear fusion in its core, back into the interstellar medium. The next generation of stars formed from gas that has been enriched by these supernovae contains slightly more of the heavier elements than the previous generation did. Each cycle of stellar birth and death adds on average a small amount of metallicity to the gas. Over billions of years, the cumulative enrichment is substantial. The Sun, having formed from gas enriched by many billions of years of previous stellar generations, is comparatively rich in metals. HD 140283, having formed from gas enriched by very few previous generations, is comparatively poor. The contrast between the two stars on this picture is essentially the contrast between gas that has been recycled many times and gas that has barely been recycled at all. Each generation contributes a small amount of heavier elements to the interstellar medium. The next generation, formed from this enriched gas, contains slightly more heavy elements than the one before. The Sun, which formed about 4.5 billion years ago, has roughly the average enrichment of its era. Younger stars are slightly richer, older stars are slightly poorer. A star with as little iron as HD 140283 must have formed very early, when the universe had not yet had time to undergo many cycles of stellar enrichment. Here is the cosmic chronometer the chemistry provides. The chemistry, in this respect, is a kind of cosmic chronometer. Stars formed early in the universe's history have low metallicity. Stars formed later have higher metallicity. The exact relationship is not perfectly linear because the enrichment was not uniform across all regions of the universe, but the general trend is robust. HD 140283's chemistry firmly identifies it as a very early formation. The implication, taken at face value, is that the star formed within the first few 100 million years after the Big Bang, when the universe had only just begun to accumulate heavier elements through the supernovae of the very first generations. Here is the broader category HD 140283 falls into. By the 1960s and 70s, careful comparison of HD 140283 to other low metallicity stars in the galactic halo had established that it was, almost certainly, a member of what astronomers call population 2. Here is the distinction Walter Baade made when he introduced the population scheme. Baade was a German-American astronomer who had taken refuge in the United States during the Second World War. His work at the Mount Wilson Observatory in California on the populations of stars in the Andromeda Galaxy gave him an unusually clear view of how stellar populations differed in chemistry and age. The classification scheme he proposed, distinguishing population 1 and population 2, became one of the foundational concepts of modern stellar astronomy. Subsequent work has expanded the scheme to include the hypothetical population 3 stars, the very first generation, formed from pristine gas with no heavier elements. But the basic population 1 to 2 distinction between the older metal-poor halo stars and the younger metal-rich disk stars remains the working framework. Population 2 stars are the older generation formed in the first billion or 2 billion years of cosmic history, before the bulk of stellar enrichment had taken place. Population 1 stars, by contrast, are the younger generation, including the Sun and most of the stars in the disk of our galaxy. The distinction was first clearly articulated by the astronomer Walter Baade in 1944, when he observed differences in the populations of stars in different parts of the Andromeda Galaxy and inferred two distinct populations with different ages and chemistries. HD 14028-3 on this picture was one of the local population 2 stars. Old, metal-poor, and almost certainly formed early in the universe's history. The population 2 identification by the second half of the 20th century was firm. The age was old. The chemistry was primitive. The star was a member of the older generation of the galaxy. Various age estimates from the 1970s and 80s placed it somewhere in the range of 12 to 15 billion years old, with substantial uncertainty. The exact value depended on which stellar models were used, which assumptions were made about composition, and which observations were included in the analysis. Different research groups working with similar data but different choices produced slightly different ages. The community had a general sense that the star was very old, but the precise value was not pinned down. The star, in this rough framework, was understood to be ancient, but the exact value of its age was not pinned down. Various age estimates from different stellar models gave overlapping but slightly different values. The uncertainties on individual measurements were typically 1 billion or 2 billion years, with various sources of systematic error that the community had not yet learned to control fully. Here is the project that brought it into focus. What changed in the early 2010s was an intensive effort led by Howard Bond and his collaborators to measure HD 140283's age with much higher precision than any previous attempt. The improved measurement would briefly change everything. The improved measurement would briefly change everything. Part 2. Reading the age of a star. To understand the Bond result, you have to understand how astronomers measure the age of an individual star, because the technique is, in some ways, more elegant than you might expect. The age of a star is not, in any direct sense, written on its surface. There is no chemical clock that ticks down. There is no obvious feature that says, in plain language, how long the star has been burning. The age has to be inferred indirectly from the star's other properties by comparing those properties to the predictions of stellar evolution theory. Here is the foundational theory the measurement rests on. Stellar evolution theory is, by the standards of modern physics, very well developed. It describes how stars of different masses, born with different chemical compositions, evolve through the various stages of their lives. It draws on nuclear physics, on hydrodynamics, on radiative transfer, and on plasma physics, all working together to describe what happens inside a star over its long lifetime. The basic equations were laid down in the early 20th century by physicists like Sir Arthur Eddington, who worked out the conditions of hydrostatic equilibrium and energy transport inside stars. They were extended through the middle decades of the century by Hans Bethe, who worked out the nuclear reactions that power stars, and Subramanian Chandrasekhar, who worked out the structure of stellar interiors. By the second half of the 20th century, the equations were reliable enough that they could be integrated on early computers to produce predicted evolutionary tracks for stars of various masses and compositions. By the early 21st century, the models were detailed enough to predict ages of individual stars to within a few 100 million years given accurate observational inputs. It describes how stars of different masses, born with different chemical compositions, evolve through the various stages of their lives. A star, when it first forms, settles on to what is called the main sequence, where it spends most of its life burning hydrogen in its core. The main sequence phase is the longest stage of any star's life. The Sun, for example, has been on the main sequence for about 4.5 billion years, and will remain there for another 5 billion years or so. The energy generated by hydrogen fusion in the core counterbalances the gravitational compression of the star's outer layers, holding the star in a stable equilibrium that lasts as long as the core hydrogen lasts. When the core hydrogen runs low, the equilibrium starts to shift and the star begins to evolve. The transition is gradual at first, accelerating as the core hydrogen depletion increases. The star's outer layers begin to expand. Its surface temperature begins to drop. Its luminosity begins to rise. The main sequence phase is, for a star like the Sun, about 10 billion years. For more massive stars, the main sequence is much shorter. For less massive stars, much longer. The duration depends sensitively on the star's mass and chemistry. Here is what happens at the end of the main sequence. After the main sequence, a star expands and brightens, becoming what is called a subgiant. The transition is driven by the gradual exhaustion of hydrogen in the core. As the core hydrogen runs out, the core itself begins to contract, while the outer layers expand and cool. The star moves, in the color magnitude diagram, from the main sequence to the subgiant region. The exact path it takes depends on its mass and composition. Lower mass stars like HD 140283 take longer to leave the main sequence than higher mass stars, but the eventual transition has the same overall shape. The duration of the subgiant phase is short compared to the main sequence phase, perhaps a few 100 million years for a star of HD 140283's mass. The star is currently in this brief intermediate phase, which is one of the reasons its age can be measured precisely. The transition from main sequence to subgiant is one of the most useful age indicators we have, because the timing depends very sensitively on the star's mass and composition. By measuring the star's current properties, particularly its luminosity and its surface temperature, and comparing those to the predictions of stellar models, you can infer where the star is in its evolutionary track. The position on the track, combined with the predicted timing of the transitions, gives the age. Here is the key feature that makes the subgiant phase useful for age measurement. For HD 140283, the relevant phase is the subgiant transition. The transition itself is geometrically distinctive in the color magnitude diagram, the standard plot used in stellar astronomy. The position of the star in this diagram, combined with its measured properties, places it firmly in the subgiant region, just leaving the main sequence. The exact position within the subgiant region depends on the star's age, in a way that the models can predict precisely. The star is just leaving the main sequence and beginning to expand into a subgiant. Its current luminosity, its surface temperature, and its mass can all be measured with appropriate care from observations. Combining these measurements with stellar evolution models calibrated for low metallicity composition gives the age. The technique works particularly well for stars in the subgiant phase because the position on the color magnitude diagram during this phase is very age-sensitive. Stars on the main sequence move slowly across the diagram. Stars in the subgiant phase move much faster. A small change in age produces a substantial change in position, which means that the age can be inferred precisely if the position is measured precisely. This is what makes HD 140283 such a useful target. Here is the elegance of the approach. It does not require any clock to be running on the star itself. There is no chemical clock, no radioactive decay clock, no clock of any kind that we can read directly from the star. It does not require any direct measurement of how long the star has been burning. It uses only the star's current observable properties plus the predictions of stellar evolution theory to derive the age. The age is, in essence, an inference, not a direct measurement. But the inference is highly constrained by the physics, and for stars whose properties are well measured, the inference can be very precise. The age, in essence, is read off a comparison between the observed star and a theoretical model. The model is a set of differential equations describing the physics of stellar interiors, integrated forward in time with the star's initial mass and composition as inputs. The output is a track in the color magnitude diagram showing where the star should be at each age. The position of the actual star on the diagram is then compared to the predicted track, and the age is the value at which the prediction matches the observation. This kind of comparison can be done very precisely if the observational properties are well measured and if the model tracks are reliable. Both conditions, in the case of HD 140283, have improved substantially over the past decade. The procedure is, in this respect, a comparison of measurement with model. The age is the value that produces the best match. The observed star is then placed on this track, and the age is the value that best matches the observation. Here is what limits the precision in practice. The accuracy of the age, however, depends on several things. The accuracy of the observed luminosity, which depends on knowing the star's distance and apparent brightness. The accuracy of the surface temperature, which is derived from the spectral type. The accuracy of the assumed composition, which affects the model predictions. The accuracy of the underlying stellar evolution models, which depend on parameterized approximations of physical processes that, at very low metallicity, may not be fully calibrated. Errors in any of these propagate into errors in the age. For a star at the bleeding edge of measurement precision, the dominant uncertainties are usually in the distance, which sets the luminosity, and in the assumed composition, which affects the model predictions. Here is why distance matters more than anything else. Distance is the single most important parameter for the luminosity. A star at twice the distance of another star with the same apparent brightness is 4 times as luminous in absolute terms. The square of distance dependence is what makes distance error so consequential for the inferred luminosity. A 10% error in distance produces a 20% error in luminosity. A 20% error in distance produces a 40% error. For age measurement at the precision bonds team was attempting, even small distance errors mattered. If you know the apparent brightness of a star and you know its distance, you can calculate its true luminosity in absolute terms. The brighter the star is in absolute terms, the larger and more luminous a model has to predict it. For a star whose age you want to measure, distance error of even a few percent can translate into age errors of 1 billion years or more. This sensitivity is what makes parallax precision so important for stellar age work. Here is the geometric technique that makes precise distance measurement possible. Distances to nearby stars in the modern era are measured by parallax. The technique was first proposed in ancient Greece, attempted unsuccessfully by Galileo and others in the 17th century, and finally succeeded for the first time in 1838, when Friedrich Bessel measured the parallax of the star 61 Cygni from a small observatory in Königsberg. The measurement, when it was published, was a substantial achievement. Bessel had spent years building up the precision required to detect the small annual shift in 61 Cygni's position. The result, with its uncertainty, was finally good enough that he could announce it with confidence. The star, by his measurement, was about 10 light-years from Earth. The exact value has since been refined, but Bessel's parallax was the first stellar distance ever measured directly. Until that point, the distances to individual stars had been complete mysteries. After Bessel, distances became measurable, and the cosmic distance ladder could begin to be assembled. The first parallax measurement showed, definitively, that 61 Cygni was at a finite distance from Earth, much further than any planet, but at a measurable distance nonetheless. The technique has, since then, been the foundation of the cosmic distance ladder, with each subsequent generation of instruments extending the technique to fainter and more distant stars. Parallax is the apparent shift in a star's position on the sky as the Earth orbits the Sun. Stars closer to us shift more, stars further away shift less. By measuring the size of the parallax very precisely, you can derive the distance, and from the distance, the absolute luminosity. The technique is geometric, model-independent, and as accurate as the precision of the position measurements. There is no theoretical assumption involved beyond the basic geometry of orbital motion. This is one of the reasons stellar parallax has been a touchstone of distance measurement for nearly 2 centuries. It depends on physics that is universally agreed upon. There is no model dependence in the parallax itself. The Earth orbits the Sun. Stars at different distances appear to shift by different amounts as the Earth moves around its orbit. The shift is the parallax. The distance follows directly from the parallax by simple trigonometry. Here is the specific instrument that produced the Bond parallax. For HD 140283, the parallax measurement that mattered in the 2012 and 2013 analysis came from the Hubble Space Telescope's Fine Guidance Sensor, which was capable of measuring stellar positions to a precision of a fraction of a milliarc second. Here is what the FGS could do that no ground-based telescope could match. By accumulating many such measurements over time, Bond and his team derived a parallax for HD 140283 that was substantially better than any previous estimate. The earlier ground-based parallax for HD 140283 had been published in the 1950s and refined in the 80s and 90s, but the precision was always limited by atmospheric effects and instrumental drift. Even the most careful ground-based measurement could not match what a space-based instrument could achieve simply because of the atmospheric noise floor. The Hubble FGS, operating above the atmosphere with very stable optics, could push the precision much higher. The instrument was originally designed to provide pointing information for Hubble itself, holding the telescope steady during long science exposures. But the same precision that allowed it to do that job also allowed it to be used in dedicated parallax campaigns to measure stellar positions to a precision of about a milliarc second. Bond's team used the instrument in this dedicated mode for years to accumulate the data they needed for HD 140283. The result was, in effect, the best parallax for any of the very oldest stars in the local neighbourhood at the time. The distance, when calculated, was about 202 light-years, with an uncertainty of about 2%. Part 3. The Bond paper. Here is the paper that brought HD 140283 to global attention. The Bond paper appeared in the Astrophysical Journal Letters in March of 2013 with the title HD 140283, a star in the solar neighbourhood that formed shortly after the Big Bang. The lead author, Howard Bond, was at Pennsylvania State University. His collaborators included Edmund Nealon at the Space Telescope Science Institute, Don Vandenberg at the University of Victoria in Canada, Gail Schaefer at the Centre for High Angular Resolution Astronomy, and Diane Harmer at the Kitt Peak National Observatory. The team brought together expertise in stellar parallax measurement, in stellar evolution modelling, and in the chemistry of metal-poor stars. Each member of the team had built a career around one of the relevant techniques. Bond, the lead author, was a long-time expert in Hubble Space Telescope photometry and astrometry. Vandenberg, the second listed author, had spent his career building stellar evolution models for low metallicity stars, with particular attention to the kinds of systematic effects that mattered for high-precision age work. Nealon, at the Space Telescope Science Institute, was responsible for the operations of the fine guidance sensor that produced the parallax. The combination of expertise was carefully assembled. No single member of the team could have done the analysis alone. The result required the parallax expertise, the modelling expertise, and the spectroscopic expertise, all working together. This kind of multi-author, multi-institution collaboration has become standard in modern astronomy, but it was particularly important for a measurement at the precision the Bond paper attempted. The combination was deliberate. To measure HD 140283's age accurately required all three. The paper's central result was the age of HD 140283, calculated from the combination of the new precise parallax, careful spectroscopic measurements of the star's surface temperature and chemistry, and the latest stellar evolution models for low metallicity composition. The team's best estimate with formal uncertainties was 14.46 billion years, with a 1 sigma uncertainty of about 800 million years. By the standards of stellar age measurement, the precision was substantial. By the standards of the central value, the result was striking. Here is the part that immediately caught the popular press. The central value, 14.46 billion years, was older than the age of the universe as derived from the cosmic microwave background, which was, at the time, about 13.8 billion years. The star, taken at the central value, was older than the universe it sat in by about 700 million years. Here is how the press cycle unfolded. The popular framing was almost inevitable. Headlines appeared. A star older than the universe. Universe younger than one of its own stars. The story spread across newspapers, magazines, science blogs, and television segments. The Bond paper itself was, characteristically of careful science, much more measured than the popular framing. The team noted, in the paper, that the age estimate had a 1 sigma uncertainty of about 800 million years. The age of the universe from the cosmic microwave background had its own uncertainty of about 100 million years. Taking the uncertainties into account, the star's age was, at the 1 sigma level, just barely consistent with the universe's age. The two estimates overlapped at the edge of their uncertainty distributions. Here is the careful version of the conclusion. There was no formal contradiction. There was, however, a tension. The central value of the star's age was higher than the central value of the universe's age. If both central values were correct, the star was older than its own universe. The popular framing had grasped this point with characteristic enthusiasm and characteristic loss of nuance. The team in the paper and in subsequent interviews was clear about what the result meant. HD 140283 was extremely old, almost certainly within a few 100 million years of the age of the universe. The star had formed very early, in the first generation or two of stars in our galactic neighbourhood. Its age, while nominally older than the universe at the central values, was not, in any robust sense, actually older. The uncertainty bands overlapped. The data was consistent with the star being slightly younger than the universe, slightly older, or essentially the same age. But the popular press, and even some commentary in the technical literature, took the result more dramatically than it warranted. Here is what happened in the broader media. For several months, HD 140283 was widely described as the star older than the universe. Articles speculated about what this meant for cosmology. Some commentators suggested that the Big Bang age estimates might be wrong. Others suggested that stellar physics needed to be revised. The discussion had a life of its own, somewhat independent of what the bond paper had actually claimed. Articles speculated about what this meant for cosmology. Some commentators suggested that the Big Bang age estimates might be wrong. Others suggested that stellar physics needed to be revised. The discussion had a life of its own, somewhat independent of what the bond paper had actually claimed. Part 4. The age that didn't quite fit. Here is the part where the careful work begins. The honest scientific situation in the months after the bond paper appeared was much more nuanced than the popular framing suggested. The science community, with the exception of a few sensational commenters, did not actually take the result as overturning cosmology. The community took it as an interesting tension that needed careful follow-up. The star's age was old, possibly slightly older than the universe at the central values, but consistent within uncertainties. The question was not whether the star was actually older than the universe. The question was whether the central values, taken at face value, were a real signal of something puzzling, or whether they were just the consequence of normal statistical variation in difficult measurements. Here is the agenda the field followed. Several things had to be checked. Here is the first of these. The first was the parallax. Bond's team had derived their parallax from Hubble Fine Guidance Sensor measurements, but parallax is one of the most demanding measurements in modern astronomy, and small systematic errors can produce age changes of significant magnitude. Other groups, looking at the same data with different reduction pipelines, found slightly different parallax values which translated into slightly different ages. The differences were small, but they were enough to matter for the question of whether the star was actually older than the universe. Here is the second uncertainty. The second was the assumed composition. Stellar evolution models for low metallicity stars depend sensitively on the assumed abundance of helium, oxygen, and other elements. Different assumptions about the composition produce different age estimates. The Bond team had used a particular set of assumptions calibrated against current understanding of the early universe's chemistry. The choices they made were defensible, and they were within the range of what other groups had used in similar work. But they were not the only choices possible. Different choices, equally defensible, would produce different age estimates. The community, in the months and years that followed, explored several alternative choices to see how the age estimate shifted. Other teams, using different assumptions, derived ages that were systematically lower by hundreds of millions of years. Whether the Bond assumptions were correct was, in 2013, an open question. Here is the third source of uncertainty. The third was the stellar evolution models themselves. The models used to interpret the observations are not perfect. They contain, in their implementations, various approximations about the physics of stellar interiors, convection, mixing, opacity, and several other processes are described by parameterized approximations that are calibrated against the Sun and other well-studied stars. The accuracy of these calibrations at very low metallicity, where HD 140283 sits, was not well established. Some commentators argued that the models were probably underestimating various physical processes and that the true ages were lower than the model predictions. The treatment of convection in particular was a known weak point. Convection in stellar interiors is, in the simplest models, parameterized by a single number called the mixing length parameter, calibrated against the Sun. Whether the same parameter applies to very low metallicity stars at the subgiant phase is not obvious. Recent work, including detailed three-dimensional hydrodynamic simulations of stellar atmospheres, has suggested that the standard mixing length parameter may overestimate convective efficiency in metal-poor stars, which would lead to systematic shifts in the inferred ages. Here is the cumulative effect of these uncertainties. Each of these uncertainties, taken on its own, was a few 100 million years. The parallax uncertainty alone could shift the age by a few 100 million. The composition uncertainty by another few 100 million. The model uncertainty by another few 100 million. When you combine them in quadrature, as the standard error analysis requires, the total uncertainty on the age becomes substantially larger than any one uncertainty alone. The Bond paper had reported a 1 sigma uncertainty of about 800 million years, but the true uncertainty, accounting for systematic effects beyond the formal 1 sigma bands, was likely larger. Combined in quadrature, they could move the central age estimate by 1 billion years or more, comfortably below the universe's age. The Bond paper had reported the age based on one specific set of assumptions and one specific reduction of the data. The choices were defensible, but they were not the only defensible choices. The community spent the next several years exploring the alternatives. Different choices, equally defensible, would give different answers. Here is what the careful response from the field looked like in practice. The community, in the months and years after the Bond paper, set about doing exactly the work needed to resolve these questions. Here is what the community did to address each of those concerns. New parallax measurements were attempted, new stellar evolution models were developed with refined treatments of the relevant physics. The work was led, in part, by Don Vandenberg himself, who had been a co-author on the original Bond paper and continued to refine the models he had built throughout his career. New treatments of atomic diffusion, of helium settling, of the various subtle physical processes that affect stellar interiors at low metallicity were progressively incorporated into the standard models. New spectroscopic analyses were carried out, with attention to systematic effects that earlier work had missed. The chemistry of HD 140283 was remeasured with improved instruments by groups around the world. Each new measurement contributed a slightly different value, with slightly different uncertainties, and the cumulative effect was to tighten the input parameters that fed into the age calculation. The age estimate for HD 140283 in the technical literature slowly drifted downward over the following years as the various uncertainties were tightened. Here is the next major contribution. By 2015, a paper by Orlor Creevy at the Côte d'Azur Observatory and her collaborators, using a different combination of stellar models and observational data, derived an age of 14.27 billion years for HD 140283, with a 1 sigma uncertainty of about 380 million years. The new central value was lower than Bond's by about 200 million years, and the uncertainty was tighter. Creevy's analysis used different stellar evolution models with refined treatments of certain physical processes that the Bond analysis had handled with somewhat older parameterizations. The result demonstrated, very concretely, how sensitive the inferred age was to the choice of stellar models. Bond's analysis was not wrong. It was just one of several reasonable choices. Creevy's analysis was a different reasonable choice. The two analyses, taken together, gave a sense of the size of the systematic uncertainty that depends on model choice. By the standards of stellar age measurement, the result was a substantial improvement. The Creevy paper was, in some ways, the first major refinement of the Bond result, and it became one of the standard references for HD 140283's age in the years that followed. Part 5. Here is where the picture got more careful. Here is what came next. The Creevy paper was not, by itself, the end of the story. Here is the broader pattern of refinement that followed Creevy. Throughout the late 2010s, multiple groups continued to refine the age estimate of HD 140283. Here is what those analyses contributed. Each new analysis introduced different inputs. Some used updated parallax measurements from the European Space Agency's Gaia mission, which began producing precise stellar positions for billions of stars in 2018 and 2020. Some used new stellar evolution models that included improved treatments of physical processes. Some used new spectroscopic measurements of the star's chemistry, which constrained the inputs to the models more tightly. Here is the pattern that emerged. The pattern, across these analyses, was consistent. The central age estimates clustered in the range of 12 to 14 billion years, with overlapping uncertainty bands. None of the modern analyses by 2025 robustly placed the star older than the universe. The original Bond result, with its central value of 14.46 billion years, was at the higher end of the distribution of subsequent estimates, but it was not the only value in the distribution. Here is the technical point that emerged from this slow refinement. The original Bond age was not wrong. It was the result of a careful analysis with the best data and models available in 2013. The subsequent refinements did not show that Bond's analysis was incorrect. They showed that several of the inputs to the analysis had uncertainties that, when accounted for more fully, broadened the age distribution. The original Bond age was not wrong. It was the result of a careful analysis with the best data and models available in 2013. The subsequent refinements did not show that Bond's analysis was incorrect. They showed that several of the inputs to the analysis had uncertainties that, when accounted for more fully, broadened the age distribution. Bond's central value was consistent with the broader distribution. Other central values derived from other analyses were also consistent. The community ended up with a probability distribution for HD 140283's age, centered somewhere around 13 billion years, with a tail extending up to about 14.5 billion years. That distribution was, on careful consideration, never actually in conflict with the age of the universe. The universe's age from the cosmic microwave background is 13.787 billion years, with very small uncertainty. Most of the probability distribution for HD 140283's age sits below this value. The tail extends slightly above it, but the bulk of the probability is below. The star, as the analyses converged in the late 2010s, was firmly identified as one of the oldest individual stars in our local neighbourhood, but not robustly older than the universe. Here is the lesson the field absorbed from this episode. Stellar ages for the very oldest stars are difficult to measure precisely. The age of the universe from independent measurements is much better constrained. When the two seem to come into conflict, the more likely explanation is usually that the stellar age has uncertainties that the standard analysis underestimates. The careful work of refining these analyses over many years is what eventually produces a coherent picture. Stellar ages for the very oldest stars are difficult to measure precisely. The age of the universe from independent measurements is much better constrained. When the two seem to come into conflict, the more likely explanation is usually that the stellar age has uncertainties that the standard analysis underestimates. The careful work of refining these analyses over many years is what eventually produces a coherent picture. The popular framing of star older than the universe was, by the late 2010s, recognized as an overstatement. The actual situation was more nuanced and more interesting. HD 140283 was, almost certainly, slightly younger than the universe. The age difference between them was small, perhaps a few 100 million years. The star had formed very early, possibly within the first few 100 million years after the Big Bang. It was, in this sense, a witness to the early universe in our own galactic neighbourhood, 200 light-years away. Part 6. The Gaia Revolution. Here is the mission that changed the field. The single most important factor in refining HD 140283's age over the years following the Bond paper was the European Space Agency's Gaia mission. Gaia was a space-based astrometry mission launched in 2013 with the specific goal of measuring the positions, distances, and motions of about 1 billion stars in our galaxy with unprecedented precision. The spacecraft was designed and built by the European Space Agency, with contributions from research institutions across Europe. Its primary instrument was a pair of telescopes, each with a 1.5 by 0.5 meter primary mirror, mounted at a precise angle to each other so that the spacecraft could continuously scan 2 patches of sky at once. By rotating slowly and scanning, the spacecraft accumulated, over its operational lifetime, billions of position measurements, each one tracking how a particular star's position on the sky shifted as the Earth orbited the Sun. The mission's first data release came in 2016. The second, in 2018, contained the first comprehensive parallax measurements for stars in our galactic neighbourhood. The third, in 2020, refined those measurements further. By the time Gaia's main mission ended in 2025, the catalogue contained position and distance measurements for nearly 2 billion stars, with parallax precisions for nearby bright stars at the 10 micro-arcsecond level. The catalogue itself, when the final data release is complete, will be one of the most ambitious astronomical catalogues ever produced. It will, almost certainly, be the standard reference for nearby star distances for the next several decades. Future astrometric missions, when they are eventually launched, will improve on Gaia in various ways, but Gaia will remain the foundational dataset for stellar age work for a long time. That precision, by historical standards, is staggering. The earliest parallax measurements in the 1830s and 40s had precisions of about 1/10 of an arcsecond. The Hipparcos mission of the 1990s improved that to about a milliarcsecond. Gaia improved it again by another factor of 100. Each generation of instruments has, in this respect, transformed what is possible. The improvements compound. What was at the bleeding edge in one generation becomes routine in the next. What was impossible in one generation becomes commonplace in the next. The history of stellar parallax measurement is, in this respect, a microcosm of how astronomy generally advances. Each new instrument extends the reach. The next generation builds on what the previous one made possible. Stellar age measurement is now in a regime that earlier astronomers could only have imagined. Here is the specific impact for HD 140283. For HD 140283, the Gaia parallax was a significant improvement over the Hubble FGS measurement that Bond's team had used. The Gaia value, when combined with the existing spectroscopic and stellar model inputs, refined the age estimate downward into firm consistency with the age of the universe. The star, on Gaia-era analyses, came out at about 13 billion years old, give or take a few 100 million years. Let me sit with that for a moment. A star, 200 light-years from Earth, formed within the first few 100 million years after the universe began, almost as old as the universe itself, visible with binoculars from any sufficiently dark backyard. The Gaia mission, more than any other single contribution, transformed the precision with which stellar ages can be measured. For HD 140283 specifically, the improvement was significant. The Hubble FGS parallax that Bond had used had a precision of about 1 milliarcsecond. The Gaia parallax for the same star had a precision of about 10 microarcseconds, 100 times better. The corresponding distance uncertainty dropped from about 2% to a small fraction of 1%. The age estimate calculated with the new distance came out somewhat lower than the original Bond value, in firm agreement with the universe's age. For thousands of other stars in our galactic neighbourhood, the improvement was equally significant. Gaia did not just improve HD 140283. It improved every nearby star with a measurable parallax. The catalogue, which is the largest ever assembled for stellar parallaxes, has transformed many subfields of nearby star astronomy beyond age determination. The whole field of nearby star astronomy was, in the late 2010s and early 2020s, repositioned around the new precision Gaia made possible. Before Gaia, distances to most halo stars were known to perhaps 10 or 20%, with corresponding uncertainties on luminosity and age. After Gaia, the same distances are known to 1 or 2%. The downstream effect on every measurement that depends on distance has been substantial. Galactic structure has been mapped in unprecedented detail. The orbital parameters of halo stars, including HD 140283, have been refined. The motion of the Milky Way relative to its dark matter halo has been measured directly. Each of these is a significant scientific advance, made possible by the same instrument that improved the HD 140283 age measurement. Here is the broader implication of this revolution. Stellar age measurement before Gaia had been a difficult and relatively imprecise enterprise. Distances were uncertain, stellar models had calibration problems. The combined uncertainties on individual stellar ages were typically 1 billion years or more. After Gaia, the dominant uncertainty became the stellar models themselves, rather than the distances. The bottleneck shifted from observational to theoretical. Improving stellar models became, in the post-Gaia era, the most useful thing the community could do to tighten ages further. Here is the transitional role the bond paper played. The bond paper, in its way, was a transitional document. It used the best parallax available before Gaia, and it pushed stellar age measurement to a level of precision that was at the bleeding edge of what was possible at the time. The result, as we have seen, generated some controversy, because the central value was older than the universe. But the controversy was, in retrospect, the kind of controversy that drives science forward. It motivated the work that produced refined parallaxes. It motivated the work that produced refined stellar models. It motivated the broader program that, by the mid-2020s, had established stellar age measurement at a much higher level of precision than was possible in 2013. Here is the deeper story behind the headlines. That, in some sense, is the deeper story of HD 140283. The star itself is ancient and remains so. What changed between 2013 and 2025 was not the star, but the precision with which we could measure it. The bond result, taken at face value, suggested an age older than the universe. The follow-up work, refining each input one by one, brought the central age into firm consistency with the universe's age. The star did not change. The science improved. The star itself is ancient and remains so. But the process of measuring its age more carefully and more precisely each year has produced a substantial improvement in our general capabilities for stellar age measurement, with implications for cosmology, for galactic archaeology, and for our understanding of the first generations of stars. Part 7. What HD 140283 actually is. Here is the picture that emerged from all this work. With the dust settled on the older than the universe controversy, what HD 140283 actually is, in physical terms, has come into much sharper focus. The star is a population 2 subdwarf, currently transitioning from the main sequence into the subgiant phase of its evolution. Its mass is about 78% of the Sun's. Its surface temperature is about 5,750 Kelvin, which is very close to the Sun's surface temperature of 5,778 Kelvin. Its luminosity, in absolute terms, is about 4.7 times the Sun's, reflecting its slightly more advanced evolutionary state. Its iron content is about 1 part in 250 of the Sun's, which is among the lowest iron contents of any star in the local solar neighbourhood. Here is the proximity that makes HD 140283 special. The fact that HD 140283 is so close to Earth, only 200 light-years away, is, in cosmic terms, remarkable. Almost all of the very oldest stars known are in the galactic halo, which is the spheroidal region of older stars surrounding the Milky Way's disk. The halo extends out to tens of thousands of light-years from the galactic centre. Most of the halo stars are very far from us. The Milky Way's halo extends to at least 100,000 light-years from the galactic centre, and probably much further. Stars in the outer halo are at distances of tens of thousands of light-years from Earth. Even with modern instruments, observing them at high precision is challenging. The combination of distance and intrinsic faintness makes detailed spectroscopy difficult, and the resulting age estimates have correspondingly larger uncertainties. HD 140283 is one of the small number of halo stars that happens to be passing through the disk on its long elliptical orbit in a phase where its position takes it relatively close to the Sun. The star is currently moving at high velocity relative to the local standard of rest, which is the signature of a halo orbit. The orbit itself is highly elliptical, taking the star out to tens of thousands of light-years from the galactic center at apocenter and bringing it back relatively close to the Sun at pericenter. We happen to be observing it during a relatively close passage. In a few 100,000 years on its long elliptical path, the star will be moving away from us, eventually reaching the outer halo before swinging back again. The orbital period is comparable to the age of the star itself. The current position is in the long sweep of HD 140283's orbit, a transient configuration. By the standards of old metal-poor stars, HD 140283 is unusually accessible. Here is what that accessibility has produced. That accessibility has made it one of the most carefully studied old stars in the literature. Hundreds of papers over many decades have analyzed various aspects of HD 140283. The early work, from the 1950s through the 70s, established its basic spectral classification, its low metallicity, and its rough age range. The middle period, from the 80s through the early 2000s, refined the chemistry, established the broader pattern of metal-poor halo stars, and produced the first, careful, evolutionary tracks. The modern era, from 2013 onward, has seen the precise age determinations, the Gaia parallaxes, and the increasingly detailed reconstructions of the star's place in the early universe. Its temperature has been measured, refined, remeasured, and refined again. Its surface gravity has been pinned down. Its detailed chemistry has been characterized at high precision. Its motion through the galaxy, including its orbital parameters as a halo star passing through the disk, has been mapped. The cumulative work by hundreds of astronomers over decades has made HD 140283 one of the better-known individual stars in the Milky Way. The combination of its proximity, its low metallicity, and its evolutionary phase that allows precise age measurement has placed it at the center of stellar age work for several decades. There are other very old stars known, some of which have been claimed to be even older, but few are as well characterized as HD 140283. The combination of proximity, brightness, and access to multiple measurement techniques makes it the standard reference object. Other ancient stars contribute their own data points, but HD 140283 is, in some sense, the anchor against which other measurements are calibrated. Here is what HD 140283 tells us about the era it formed in. The chemistry, when measured carefully, encodes information about both the gas the star formed from and the supernovae that enriched that gas. Different elements behave differently in the supernovae of different progenitor stars. Massive stars produce different element ratios than intermediate mass stars. Pair instability supernovae, which only occur for very massive POP3 stars, produce a distinctive pattern that ordinary core collapse supernovae do not. By comparing the observed pattern in HD 140283 to the patterns predicted by different progenitor scenarios, astronomers can constrain what kinds of progenitor supernovae must have contributed to the gas the star formed from. The constraints are not perfect, but they are genuinely informative. The star's chemistry implies that it formed from gas that had been enriched by supernovae of an earlier generation, but only minimally. The ratio of various heavy elements in HD 140283's atmosphere, when measured carefully, is consistent with enrichment by population 3 supernovae, the explosions of the very first generation of massive stars. Here is the cycle that creates new generations. The first stars formed from pristine gas with no heavy elements at all, exploded as supernovae and seeded the surrounding gas with the first heavier elements. The supernovae themselves, beyond their immediate dramatic visibility, are the engines that produced almost all of the carbon, nitrogen, oxygen, and other heavier elements we know about. Without them, the gas in the universe would have remained essentially pristine, with only hydrogen, helium, and traces of lithium produced in the Big Bang itself. Every heavier element in your body, every atom of carbon in your DNA, every atom of iron in your blood was produced inside a star and scattered into the interstellar medium when that star died. The supernovae of the first generations are the chemical ancestors of every solid object that has ever existed. Stars like HD 140283 formed from that slightly enriched gas in the next phase of cosmic history. The star, in this sense, is a kind of fossil of the first generation. Not the first generation itself, which we have never directly observed, but the immediate descendants formed from material that the first stars produced. Here is the deeper resonance of all this. This is, in itself, a profound thing. We have in our own galactic neighbourhood 200 light-years from Earth, a star whose composition encodes information about the very first stars in the universe. We can study it in detail with backyard telescopes. We can measure its chemistry, its temperature, its luminosity, its motion, all to high precision. The information about the early universe that the star carries is right there, in the data, available to be read. We have in our own galactic neighbourhood 200 light-years from Earth, a star whose composition encodes information about the very first stars in the universe. We can study it in detail with backyard telescopes. We can measure its chemistry, its temperature, its luminosity, its motion, all to high precision. The information about the early universe that the star carries is right there, in the data, available to be read. Part 8. The first generation question. Here is the population of stars that came before HD 140283. The very first stars in the universe, the so-called population 3 stars, have never been directly observed. They are believed to have formed about 150 million years after the Big Bang in the densest regions of the early universe, from gas containing essentially only hydrogen and helium with no heavier elements at all. They were, by the most current models, very massive, with typical masses of perhaps 100 or even 1,000 times the mass of the Sun. The reason for the unusual masses is the lack of heavy elements in the gas they formed from. Heavier elements provide important cooling pathways during cloud collapse, allowing the gas to lose energy efficiently and fragment into smaller pieces. Without those elements, the cooling is much less efficient, and the gas clouds tend to collapse into larger, more massive stars. Population 3 stars, on this picture, were born much larger on average than the stars we see in the present universe. The largest of them may have been many hundreds of solar masses each. They burned hot and bright. They lived only a few million years before exploding as supernovae. Massive stars in any era of the universe have very short lives. The Sun, with its modest mass, will live for about 10 billion years. A star 100 times the Sun's mass lives for only about 1 million years before exhausting its core hydrogen and undergoing the chain of evolutionary stages that ends in a supernova explosion. Population 3 stars with masses in this range lived very brief lives. Their entire collective contribution to cosmic history happened in the first 100 million years or so after they formed. Then they were gone. They are, in the universe today, all gone. Their original mass has been recycled into later generations of stars in the interstellar medium. Here is the technique that gives us indirect access to population 3. What we can do, instead of observing population 3 stars directly, is study their chemical fingerprints in the surfaces of later generations. The technique is, in essence, archaeological. We dig through the chemical record of old stars and reconstruct, from the patterns we find, what kind of progenitors must have produced them. The resulting picture is approximate, but it is genuinely informative. It tells us in some detail what the very first stars must have been like. The supernovae of population 3 stars produced specific patterns of heavier elements, with distinctive ratios that depend on the mass of the progenitor star and the details of the explosion. The next generation of stars formed from material enriched by these supernovae carry those patterns in their atmospheres. By measuring the chemistry of very old stars like HD 140283, we can reconstruct, indirectly, what kind of population 3 supernovae produced the material they formed from. The reconstruction is not perfect, because different progenitor scenarios can produce overlapping element ratios, and because the gas that any particular star formed from may have been enriched by multiple supernovae of different progenitor types. But the broad outlines are well constrained, and the constraints have grown sharper as more old stars have been catalogued and analysed. Here is what the chemistry of HD 140283 tells us about its progenitor supernovae. The ratios of various heavy elements in the star's atmosphere are consistent with enrichment by a small number of moderate mass population 3 supernovae, rather than by the very massive pair instability supernovae that some models predict for the very first stars. The implication is that the immediate progenitors of HD 140283 were not the most massive population 3 stars, but rather the somewhat less massive ones, perhaps in the range of 15 to 40 solar masses. Stars in this mass range explode as conventional core collapse supernovae, producing element ratios that match what we see in HD 140283's atmosphere. The match is not perfect, but it is consistent with the broad pattern, and other interpretations would require either much more massive or much less massive progenitors than the standard core collapse range. Stars at much higher masses would have produced different ratios, characteristic of pair instability supernovae, which are not observed in HD 140283. This kind of inference drawn from the chemistry alone is what gives us our best window into what the very first stars must have been like, even though we cannot see them directly. These would have been very early in cosmic history, but not necessarily the very first stars. Here is why this approach matters, even though we cannot see population 3 directly. This kind of inference, drawn from careful spectroscopy of very old stars, is one of the most powerful tools we have for understanding the first generation. We cannot see population 3 stars directly, but by reading their chemical signatures in the atmospheres of their immediate descendants, we can reconstruct, in some detail, what they were like and how they lived. HD 140283, in this respect, is one of the most informative archaeological records we have of the very first stars. Here is the broader catalogue of ancient stars HD 140283 belongs to. Other very old metal-poor stars have been catalogued in subsequent surveys. The field of ancient star searches has been one of the more active areas of nearby star astronomy over the past 3 decades. Surveys like the HK survey of Beers, Preston and Schechtman in the 1980s and 90s, the Hamburg/ESO survey, and more recent efforts using SDSS and SkyMapper data have together identified thousands of metal-poor halo stars suitable for detailed follow-up. Some of them have been claimed to be even more chemically primitive than HD 140283. Here are some of the other extreme cases. SMSSJ 03130.3 6-6708339.3, a star in the Sculptor constellation, has the lowest known iron abundance of any star ever measured, with iron content less than 1 part in 10 million of the suns. The star was discovered in 2014 by a team led by Stefan Keller, using the SkyMapper survey at the Siding Spring Observatory in Australia. Its extreme metal poverty makes it one of the most chemically primitive stars ever studied. The implication is that it formed from gas that had been enriched by, at most, a single progenitor supernova, possibly the very first generation. HE1523-0901 in Libra has been measured to have an age of about 13.2 billion years, based on radioactive thorium decay, rather than stellar evolution models. The thorium technique relies on detecting the small remaining quantity of radioactive thorium-232 in the star's atmosphere and comparing it to the abundance of stable elements that were produced alongside it in the original supernova. Since thorium decays with a known half-life of 14 billion years, the ratio of remaining thorium to stable products gives a direct age. This is, in some ways, the cleanest age measurement possible because it uses a known nuclear decay rather than indirect inferences from stellar evolution. The technique has been pioneered by astronomers like Anna Friebel at MIT and Norbert Christlieb at Heidelberg, and applied to a small but important sample of metal-poor stars. These stars, taken together, are part of an emerging archive of ancient witnesses, distributed throughout the galactic halo, each carrying chemical information about the very early universe. The combined catalogue is, in this respect, a kind of distributed cosmological archive. No single star tells the whole story, but many stars observed together are slowly building up a coherent picture of the very early universe, encoded in their atmospheres, accessible through careful spectroscopy. Part 9. Why this matters for cosmology. Here is the cosmological role HD 140283 plays even after the controversy faded. The age of HD 140283. Even after the careful refinements that brought it down from the original Bond central value, is still useful for cosmology. Here is the cross-check that stellar ages provide. The reason is that it provides an independent lower bound on the age of the universe. The universe must be at least as old as its oldest stars. If the best stellar age estimates for HD 140283 are around 13 billion years, then the universe must be at least 13 billion years old. This is independent of the cosmic microwave background measurement of the universe's age. It comes from a completely different physics, applied to completely different observations. Here is why this kind of cross-check matters. Here is the methodological point. The cosmic microwave background gives a very precise age for the universe, but it does so within a particular cosmological framework. The framework, called lambda CDM, has been extensively tested against many other observations, but it has never been tested directly against an independent measurement of the universe's age. Stellar age measurements provide that independent test. If stellar ages and cosmological ages were systematically inconsistent, that would be a serious problem for one or both methods. If the framework is wrong, the inferred age could be off. Stellar age measurements provide an independent test using different assumptions and different physics. If stellar ages and cosmological ages were systematically inconsistent, that would be a serious problem for one or the other. The fact that they are, on careful work, broadly consistent is itself a confirmation of both. Cosmology and stellar astronomy are, in this respect, two completely different methods of measuring the age of the universe, and they agree. That kind of agreement between methods that depend on entirely different physics and entirely different observations is the kind of redundant confirmation that makes scientific knowledge robust. Here is the moment of tension. Here is the moment of tension. The Bond paper, in this respect, was a moment when this cross-check briefly appeared to be in trouble. The central age of HD, 140283, was older than the central age of the universe. If both central values had been correct, with small uncertainties, the implication would have been that something serious was wrong. Either the standard cosmology was off, allowing for an older universe than the cosmic microwave background suggested, or the stellar physics was off, allowing for a younger star than the stellar models predicted. Either way, something would have needed substantial revision. If both central values had been correct, with small uncertainties, the implication would have been that something serious was wrong. The subsequent refinements, which brought the stellar age into firm consistency with the universe's age, eased the tension. But the moment of tension was, in itself, scientifically valuable. It motivated the careful work that produced the refinements. It demonstrated the importance of systematic uncertainties. It showed how the field reacts when an apparently impossible result appears. Here is the broader implication. Stellar ages and cosmological ages are not the same kind of measurement. They use different physics. They have different uncertainties. They are derived from different observations. The fact that they agree, on careful work, to within a few 100 million years is one of the more remarkable features of modern cosmology. It is the kind of agreement that is possible only because both methods are, in their broad outlines, correct. Part 10. What HD 140283 still teaches us. Here is what continues to come out of HD 140283 each year. In the years since the Bond paper, HD 140283 has continued to be studied. Its age estimates have continued to be refined. New observations with new instruments have continued to add data points. The picture, in 2025, is more detailed than it was a decade ago. The star is firmly identified as one of the oldest individual stars in our local neighbourhood. Its age, by the best modern estimates, is somewhere around 13 billion years, with uncertainties of a few 100 million years. The original Bond central value of 14.46 billion years is at the high end of the modern probability distribution, but not the central value of any modern analysis. Here is what the star still teaches us. The careful science of measuring stellar ages at the level of precision required to compare individual stars to the age of the universe is genuinely difficult. The various uncertainties in distance, in composition, in stellar models all have to be carefully controlled. Small errors in any of these inputs can produce significant errors in the inferred age. The work of pinning down stellar ages, even for the most carefully studied stars, remains an active area of research. Here is the practical implication of the Gaia revolution. The Gaia mission, by providing precise parallaxes for billions of stars, has shifted the bottleneck from distance measurement to stellar modelling. For most of the history of stellar age determination, the dominant uncertainty has been the distance. Now, the dominant uncertainty is the model. Here is the bottleneck for the next decade. The next decade of work in stellar age measurement will almost certainly be dominated by improvements to stellar evolution models. New treatments of physical processes like convection, atomic diffusion, and rotation are gradually being incorporated into the standard models. Each refinement tightens the ages slightly. The cumulative effect over the next 10 or 20 years will be substantially improved age measurements for the oldest stars in our galactic neighbourhood. Here is one more thing the star teaches us, which is more philosophical. Here is the deeper lesson about science journalism. The popular framing of star older than the universe was, in retrospect, a substantial overstatement of what the actual measurement showed. The bond paper itself was careful, measured, and quantitatively honest about its uncertainties. The press coverage took the central value, ignored the uncertainties, and produced a story that, technically, was incorrect. The pattern in modern science journalism is recurrent. Dramatic results get amplified, careful refinements get less attention. The slow, careful, long-term work of pinning down accurate values often produces a more nuanced picture than the original headline implied. Big science results, particularly results that involve apparent paradoxes or tensions with established theory, get amplified by the popular press in ways that often distort the underlying meaning. The amplification is not malicious. Most science journalists are doing their best to translate technical findings into accessible language, but the translation, in passing through several layers of editorial decision-making about what makes a compelling headline, often loses the careful, conditional structure that the technical community uses. The careful response from the community, which acknowledged the tension while emphasizing the uncertainties, eventually produced a more accurate picture. Here is the disclaimer that needs to be on the table. I am not saying that the bond paper was wrong. I am not saying that the popular coverage was malicious. I am not saying that the original headline was meaningless. What I am saying is that the actual scientific situation behind the headline was always more nuanced than the headline could capture. The star was always within the uncertainty bands of being slightly younger than the universe. The headline made it sound like the star was robustly older. The truth was always closer to the careful interpretation than to the dramatic one. Here is the methodological lesson that I want to leave you with before we move on. The way stellar ages are measured is, fundamentally, a layered inference. There is the observation, which produces a set of numbers with their associated error bars. There is the model, which translates those numbers into a physical picture of the star. There is the calibration, which ties the model to a set of reference observations whose interpretation is itself model-dependent. Each layer carries its own uncertainties. Each layer interacts with the others in ways that are not always linear. The total uncertainty on a derived quantity, like an age, depends on a careful propagation through every layer in the chain. Here is what that means in practice. When a paper publishes an age with an uncertainty of plus or minus 800 million years, the 800 million years is itself an estimate, derived from a particular accounting of which uncertainties are dominant and how they combine. A different accounting by a different team may produce a different uncertainty estimate, even using the same underlying observations. This is not a flaw of the method. It is the nature of inference under partial information. The community, over decades of work on individual stars like HD 140283, has gradually converged on best practice accounting procedures. The convergence is not yet complete. It will, in all probability, never be entirely complete. Different teams, with different stellar evolution codes and different calibration choices, will continue to publish slightly different central values and slightly different uncertainty bands for the same star. The shape of the picture, on average across the community, will continue to sharpen. The picture for HD 140283, in particular, has sharpened substantially since 2013. It will continue to sharpen year by year as the various inputs are refined. Part 11. The stellar archives in our neighbourhood. Here is the broader context. HD 140283, taken in the broader context of stellar archaeology, is one of an emerging family of ancient witnesses. The galactic halo of the Milky Way contains, by the most current estimates, perhaps a few thousand stars with ages above 13 billion years. These stars are the survivors of the very early epochs of our galaxy's history. Each one, when carefully observed, contributes a data point to the picture of how the Milky Way assembled itself in its first few billion years. The galactic halo, the spheroidal region of old stars surrounding the Milky Way's disk, contains a substantial population of very old metal-poor stars. Most of them are too distant to study in detail. A small number, like HD 140283, happen to be in orbits that bring them through our local neighbourhood, where they can be observed at high precision. Here is the relative ranking among ancient stars. Among the very oldest stars known, HD 140283 is the most thoroughly characterized. There are other ancient stars with claimed ages above 13 billion years, but most of them are at distances that make precise age measurement much harder. HD 140283 sits in the sweet spot of being old enough to be cosmologically interesting, close enough for precise measurement and bright enough for detailed spectroscopy. The combination is unusual. Other stars with different histories, different chemistries, different ages are also being studied. The metal-poor halo of the Milky Way contains, by some estimates, a few thousand stars with ages above 13 billion years. Each one, when carefully measured, contributes a data point to the picture of the early universe. The combined catalogue, after 30 years of patient work, is one of the better resolved historical records in modern astronomy. The first few 100 million years of cosmic history are slowly coming into focus, not as a single snapshot, but as a mosaic of many individual stellar witnesses, each one contributing its own piece of the story. HD 140283 is one of the more important pieces, but it is not the only piece. The mosaic is built from many stars, each contributing its own spectroscopic, photometric, and astrometric data, gradually building up the full picture. The first, few 100 million years of cosmic history are slowly coming into focus, not as a single snapshot, but as a mosaic of many individual stellar witnesses, each one contributing its own piece of the story. The combined statistics, drawn from many such stars, are slowly building up a detailed reconstruction of the chemistry and dynamics of the first few billion years of the Milky Way's history. By comparing the chemistry of stars in different orbital families, astronomers can trace which stars formed in our galaxy and which were absorbed from smaller satellite galaxies that the Milky Way merged with billions of years ago. By comparing the ages of stars in different parts of the halo, the timeline of galactic assembly can be reconstructed. The picture, after 30 years of patient work, is far more detailed than it was when the survey programs began. Here is the field that has emerged from this kind of work. It is called stellar archaeology, and it uses the chemistry of old stars to reconstruct the conditions in which they formed. The discipline grew out of the metal-poor star surveys of the 1980s and 90s when astronomers like Timothy Beers, John Norris, and Stephen Ryan systematically searched the galactic halo for the most chemically primitive stars. The work continues today, with major contributions from Anna Friebel at MIT, Norbert Christlieb at Heidelberg, Waco Aoki at the National Astronomical Observatory of Japan, and many others. The combined catalogue of metal-poor halo stars is one of the most carefully assembled archaeological records in modern astronomy. The technique has, over the past 2 decades, produced detailed maps of the early Milky Way's chemical evolution. The first generation of supernovae, which seeded the gas with the first heavy elements, can be reconstructed indirectly through the patterns of those elements in old stars. The merger history of the Milky Way, including the various smaller galaxies that were absorbed into it billions of years ago, can be traced through the populations of old stars in different orbital families. The whole archaeological picture of our galaxy's early history is being built up, star by star, from observations of the very oldest survivors. HD 140283 is, in this picture, one of the most important individual records. Its age, its chemistry, its motion, all encode information about the early Milky Way and the early universe. The careful work of measuring these properties over the past several decades has been one of the more productive enterprises in modern stellar astronomy. Here is the parallel with our previous evening's story. The galaxy JADES-GS-Z14-0 at Z equals 14.32 is a record of the very early universe in a galaxy 13.5 billion light-years away. HD 140283 is a record of the very early universe in a star 200 light-years away. Both are ancient, both carry information about the first few 100 million years of cosmic history, but they are very different kinds of records, accessed through very different techniques. JADES-GS-Z 14-0 is studied through the most distant photons we can detect. HD 140283 is studied through the chemistry of a star you can see with binoculars. The same era, looked at from 2 completely different angles, both contributing to the picture. Part 12. The view from the local neighbourhood. Here is the asymmetry that makes HD 140283 different from JADES-GS-Z 14-0 in our previous evening's story. There is a particular property of HD 140283 that I find genuinely moving when I sit with it carefully. Here is the asymmetry between the light and the star itself. The star is 200 light-years from Earth. Light from the star reaching us tonight has been travelling for 200 years. The photons that arrive on Earth tonight left the star around the year 1825. That is recent. By cosmic standards, that is essentially zero lag. The star we see tonight is, in any meaningful sense, the star as it is now, but the star itself is 13 billion years old. The photons we receive tonight were emitted in the last few hundred years of a 13 billion year stellar lifetime. The star has been burning in some form since long before our solar system existed. It was already nearly its current age when the Sun first lit up 4.5 billion years ago. It was already nearly its current age when the Earth first formed. It was already nearly its current age when the first life appeared on Earth, when the dinosaurs lived and died, when our own primate ancestors first walked. The star has been there, on its slow elliptical halo orbit, throughout almost the entire history of everything we recognize. Here is the asymmetry between cosmic time and stellar time. The galaxies we see at high redshift, like JADES-GS-Z14-0, are old in the sense that the light from them is old. We are seeing them as they were 13.5 billion years ago. The stars we see in our own neighbourhood, like HD 140283, are old in a different sense. We are seeing them as they are now, but they are individually 13 billion years old. The same total age, but accessed through very different paths. Here is the practical observing experience. The light from HD 140283 on a clear winter evening in the southern part of the northern hemisphere is reaching binoculars across the world. Anywhere on Earth where the sky is dark enough, where the constellation Libra is above the horizon, where the observer has the right star chart and the right binoculars, the photons from HD 140283 are arriving in real time. They have been arriving every clear evening for centuries. They will keep arriving for as long as the star burns and the Earth turns. The continuity of arrival is one of the more underappreciated features of nearby star astronomy. The ancient star is not, in any sense, hiding from us. The ancient star is, in every clear evening, available to be seen. Anyone with the right star chart, the right binoculars, and the right patience can find the star and look at it. The photons reaching the eye of the observer are from a star that has been burning since the early universe. The light is, at the moment it reaches the eye, just a few hundred years old. The star is 13 billion. The combination is, when you sit with it, one of the more remarkable things you can do with a pair of binoculars on a dark night. Here is the practical reality of looking at HD 140283 yourself. Most amateur astronomers, even those who know HD 140283 by reputation, never actually take the time to look at it. The star is too faint to be impressive. Through binoculars, it just looks like another point of light, indistinguishable from any other star of similar brightness. There is nothing visible to the eye that conveys its history. The chemistry is invisible. The age is invisible. The information about the early universe is invisible. All you see is a small, dim star. But you are seeing it. The light from one of the oldest objects in our galactic neighbourhood is, in that moment, falling on your retina. The chain of photons from HD 140283 to your eye is unbroken. From the surface of the star to your retina, a path through 200 light-years of empty interstellar space, with nothing in between to interrupt the journey. The photons travelled through the same gas that all the other photons of the night sky travelled through, but each one carries the specific fingerprint of the star it left from. Your eye, in collecting them, is collecting a small piece of one of the oldest individual objects in our galactic neighbourhood. The star, which has been burning since almost the beginning of cosmic history, is, in that moment, in your direct visual experience. That is, in some sense, the deepest thing this whole story is about. Part 13. Where to look. Here is where Libra sits in the sky. The constellation Libra is in the spring sky in the northern hemisphere and the autumn sky in the southern hemisphere. Libra has, in human history, an unusual identity. It is one of the few constellations in the zodiac that does not represent an animal or a person. Libra represents the scales of justice. The Greeks originally considered the stars of Libra to be part of Scorpio, representing the claws of the scorpion. The Romans separated them into a distinct constellation and gave it the scales identity, possibly because the constellation rises around the autumnal equinox, when day and night are in balance. It sits between the much brighter constellation Scorpio to its east and Virgo to its west. Libra is one of the dimmer constellations in the zodiac, with no stars brighter than about magnitude 2. Most casual observers looking at the spring sky do not particularly notice it. HD 14028-3 is in the northern part of the constellation, at right ascension 15 hours and 43 minutes and declination -10 degrees and 46 minutes. The exact coordinates plugged into any backyard astronomy app will produce a location on the sky map. The star is at apparent magnitude 7.2, which means it is just below the threshold for the unaided eye, but easily visible through any modest amateur instrument. Here is how to actually find it. To find HD 140283 in the sky requires a small telescope, or good binoculars, and a clear, dark night. The procedure is straightforward. First, find Libra in the sky by locating Scorpio to its east and following the line of bright stars westward. Then, within Libra, locate one of the brighter stars as a starting point. Use a star chart, on paper or on a phone, to navigate from the starting star to the position of HD 140283. The star will appear through binoculars as a small dim point of light, indistinguishable from many other faint stars in the same field. If you have access to a moderate-sized telescope, perhaps 8 inches or larger, the star will appear slightly brighter and slightly more separated from the surrounding field. With a moderate-sized backyard telescope and patience, the star is genuinely accessible. It is, by accident of position and brightness, one of the few ancient stars in the universe that you can directly observe from your own back garden on a clear evening, with equipment that costs less than a used car. Higher magnification will not reveal any visible structure, because the star is, like all stars, just a point of light at any reasonable telescope size, but it will be there, in the center of the field, with the same chemistry and the same age that the careful spectroscopic and parallax measurements have determined. Looking at it directly, you would not see the chemistry. You would not see the age, you would just see the photons that arrived after their 200-year journey, falling on your retina, indistinguishable from photons from any other star. But the photons themselves are carrying the information, whether or not you can read it directly. There is something quietly remarkable about being able to look at this object with backyard equipment. Most of the very old stars known to astronomy are far too faint for amateur instruments. Most are at distances of thousands of light years in the deep galactic halo. They require professional telescopes with long integration times to study at any meaningful precision. They cannot be photographed by an amateur, even with a substantial backyard setup. They cannot be observed visually in any meaningful way. They are, in this respect, the property of professional astronomy alone. HD 140283 is the rare ancient star that is right at our doorstep, accessible to anyone with the patience to find it. Here is what the proximity gives us, in concrete terms. There is, in this fact alone, a small kind of democracy of cosmic observation. The most carefully studied old star in our galactic neighbourhood is, by accident of geometry, also the most accessible to amateur observers. Anyone who wants to look at the local cosmic memory can do so, with equipment that is, by professional standards, modest. That kind of accessibility is rare in modern astronomy, where most cutting-edge observations require space-based instruments or very large ground-based telescopes that no amateur can replicate. There is something fitting about that. The star whose age stress-tested cosmology, the star that for a few months in 2013 made the popular press wonder whether the Big Bang was wrong, the star that has been the subject of dozens of careful refereed papers in the major astrophysics journals, is also a star that any patient amateur with a small telescope and a clear evening can find for themselves. The chain from professional observatory to backyard binocular is, in the case of HD 140283, unusually short. The same photons that the Hubble Space Telescope used in 2013 to measure the parallax to 1 part in 800 are the photons that an amateur observer in their own back garden can let fall on their own retina on a clear spring evening with their own eyes. Part 14. Coming Home. Here is the long arc that produced this story. We did not set out to find a star older than the universe. We set out, in the early years of the 20th century, to catalogue the bright stars of the sky. The Henry Draper catalogue listed HD 140283 as one of millions of catalogue objects. For decades, the star was unremarkable. It was just one of the millions of objects in the catalogue. Various stellar surveys, photometric catalogues, and spectroscopic studies in the early to mid-20th century included HD 140283, alongside many other stars. The star contributed data points to broader surveys, but did not, on its own, attract particular attention. Even after the early measurements established that it was metal-poor, it was, for the broader astronomical community, just one example among many of an old halo star. It did not become particularly famous until the early 2010s, when the careful age determination put it in the spotlight. The work of measuring its chemistry in the mid-20th century established that it was very metal-poor and almost certainly very old. The work of measuring its age more carefully each decade gradually pinned down a value that, in 2013, briefly appeared to be older than the universe itself. Here is what happened in the public imagination. The popular framing of star older than the universe caught the imagination of the world for a few months in 2013. Articles were written, television segments were aired, various commentators speculated about what it meant. Some suggested cosmology was wrong, some suggested stellar physics was wrong, some suggested both. The actual scientific situation, as we have walked through, was much more nuanced than any of these dramatic framings allowed. Here is what the careful follow-up actually showed. The careful follow-up in the years that followed showed that the apparent paradox was a consequence of taking the central values of difficult measurements too literally. The star, on subsequent analyses, was firmly within the uncertainty bands of being slightly younger than the universe. The paradox dissolved. The star remained. Here is the consensus picture today. What HD 140283 actually is, by the best modern measurements, is one of the oldest individual stars we know about, almost as old as the universe itself. 200 light-years from Earth, visible with binoculars on a dark night. A witness, in our own galactic neighbourhood, to the very early universe. A star whose chemistry encodes information about the first generations of stars and supernovae. A star whose orbital motion marks it as a member of the galactic halo, formed in the very early epochs of Milky Way history. A star that, by the standards of any other star in our local stellar neighbourhood, is genuinely ancient. A star that formed within the first few 100 million years after the Big Bang and has been quietly burning on its long elliptical halo orbit ever since. The constellation Libra is in the spring sky in the northern hemisphere. On a clear evening, when conditions are right, you can find HD 140283 in your binoculars and look at it, knowing that the small dim point of light you are seeing is one of the oldest objects in our local universe. The star is, in some sense, the universe's local memory. It has been there since almost the beginning, in our own galactic neighbourhood, the whole time. There is one final thought I want to share before sleep about the comparison between HD 140283 and JADES-GS-Z14-0 from our previous evening. Both are records of the very early universe, both formed within the first few 100 million years after the Big Bang. Both, in their different ways, are among the oldest individual objects we have ever directly studied, but they could not be more different in how they reach us. JADES-GS-Z14-0 is studied through photons that have travelled for 13.5 billion years across the expanding universe to reach us, faint and stretched, in a single galaxy at the edge of time. HD 140283 is studied through photons that have travelled for 200 years across our local neighbourhood, bright and clear, in a star you can find with binoculars. Same era, same age, two completely different angles on the same cosmic story. The contrast is, in its way, the deepest illustration of what astronomy has become in our era. The same cosmic event from two completely different vantage points, both contributing to the picture. You can let it go for tonight. Here is what continues regardless of whether anybody is paying attention. The work of measuring stellar ages continues. The Gaia mission has produced its final data release. New stellar evolution models are being developed. The age of HD 140283 will continue to be refined year by year as the various inputs are tightened. Here is the timeline for that. By 2035 or so, the age estimate may be precise enough that the original Bond controversy is fully retired into the historical record. The next generation of astronomers working through the late 2020s and early 2030s will inherit the picture we are beginning to assemble now. They will refine it further. They will publish papers that, in due course, will be cited by their own students. The slow accumulation of stellar age measurement over the course of a century will continue, with HD 140283 serving as one of the central reference objects throughout. Until then, the star sits in our sky 200 light-years away, with its uncertain age, in its careful mathematical relationship to the age of the universe. The work continues because that is what science does. The instruments are still pointed. The data is still being analysed. The papers are still being written. The picture, year by year, gets a little sharper. The story, slowly, gets a little more accurate. Good night. Sleep well. The oldest neighbour is still in its orbit. The light is still arriving. The age tonight is what it has always been. Here is the last small thing to hold before sleep. The star has been there in its long elliptical halo orbit for almost the entire age of the universe. It was there before the Earth formed. It was there before the Sun formed. It was there before the Milky Way's disk fully assembled itself. It was there in the very first epochs of cosmic history, when the universe was a few 100 million years old, and the first generations of supernovae had only just begun to seed the gas with the elements that would, much later, find their way into your bones. It is still there now. It will still be there tomorrow morning when you wake up. It will still be there next year and next decade, and at the end of the century. The star is, in this respect, the slowest clock in the local universe. Whatever is happening tonight in your room or in your life, the star keeps its own time, on its own scale. There is something quietly steadying about that. Sleep well. The star is older than we are. The universe is older than the star. Both are still here. The light from HD 140283 reaching binoculars across the world tonight is, in its own quiet way, the deepest archive we have. It has been arriving every clear evening for thousands of years. It is arriving now. It will keep arriving for as long as the star burns and the earth turns. Sleep well. The oldest neighbour has not yet finished its long lap of the galaxy. The light keeps coming.